The sky is an ideal playground for adventure, but it can quickly turn into a very uncomfortable place. This is why learning how to fly also requires a comprehensive understanding of meteorology. Before tackling the broad topics of macro and micrometeorology, you need to be aware of the following basic principle. Warm, humid air is lighter than cold, dry air. Keeping this physics rule in mind, let's take a look at some meteorological fundamentals that will help you better understand your future playground in the sky. The atmosphere is composed of perpetually moving air masses. To better understand these incessant movements, let's take a look at a model of our atmosphere from a planetary perspective. Our planet has two major air mass zones. The polar air zones, located at the poles of the Earth, which extend into some of Earth's temperate regions, and the tropical air zone forming a belt around the equator, which also extends into Earth's temperate regions. Why is there a difference between the temperatures of the polar zones and the zone near the equator? The sun's rays are parallel to one another when they reach the Earth, but not all of them arrive at a 90-degree angle because the Earth is a sphere. As a result, the polar regions are put at a disadvantage since at high latitudes, the same amount of radiant energy from the sun is spread out across a larger surface than at the equator. By scaling this surface to the length of a segment, the difference becomes clear. Segment A is longer than segment B. As a result, the ground located in the polar zones heats up less, as does the mass of air directly above it. And since cold air holds little water vapor, the polar air mass is relatively dry. On the other hand, the ground located in the tropical air mass zone is heated more efficiently. The heat energy from the ground then warms the air mass directly above it, and because a warm air mass holds more water vapor than a cold air mass, it will be more humid. The transfer of heat energy between the sun and the ground, or the ground and the air, deserve a few explanations. First off, radiation. Radiation is the process by which the infrared energy emitted from the sun is directly absorbed by an exposed solid, in this case the ground. This type of energy transfer primarily works with solids. It's far less efficient with fluids or gases. The second type of energy transfer is conduction. As far as solids are concerned, this is the easiest way to transfer heat. If one end of an iron bar is heated, the heat will rapidly spread to the other end. In our example, involving the ground and the air, the energy transfer takes place between two different substances, a solid and a gas. Having stored up thermal radiation from the sun, the ground then heats the air it is in direct contact with. And finally, convection. This type of molecular energy transfer occurs in fluids such as gases or liquids. Air masses transfer heat between one another through convection. A warm layer of air will expand and rise. Now that you know a little more about the types of heat transfer from one substance to another, let's look at the two air masses found at our latitude. On the one hand, you have a mass of cold, dry air called the polar air mass. On the other hand, a tropical air mass, composed of warm, humid air that is less dense than the former. These two air masses, though radically different in regards to their temperatures and humidity levels, remain adjacent to one another without ever mixing. The boundary between the two air masses is called the polar front. As long as these air masses move parallel to one another, the polar front is said to be stationary. But in many cases, cold and warm air masses overtake one another, causing unstable wave-like undulations along the polar front. As the amplitude of an undulation between the two masses increases, a low-pressure system develops. Weather forecast bulletins on television shows us satellite images of these low-pressure systems. The white clouds are spiraling around a low-pressure center because of the thermal contrast between the cold and warm fronts. The center of this low-pressure system will grow and evolve. These systems are responsible for the weather conditions in our temperate regions. By observing the evolution of a weather system from the ground, we can make predictions about how the weather is going to change and consequently better plan for those changes. What can we observe from the ground? The arrival of a warm front. A warm air mass will rise above a cold air mass because it is less dense. The warm front has an almost vertical slope and moves slowly. The ground temperature increases slightly. The arrival of a warm front is first noticeable by the formation of clouds at very high altitudes, such as cirrus or cirrostratus. Then, as the warm front advances, rain clouds will begin to form at lower altitudes. Then, the cold front moves in quickly, behind the slower-moving warm front. The mass of cold air being denser, it undercuts the warm air, forcing it to rise. The warm air condenses quickly and abruptly, causing storm clouds such as cumulonimbus to form. The air mass becomes quite unstable. Ground level temperatures decrease. When a cold front catches up with a warm front, it's called an occluded front. After the cold front moves away, the sky clears up. Then, a high-pressure system, also known as an anticyclone, sets in. The front having passed, the sun's rays now are able to penetrate the clear skies and heat the ground, creating updrafts of air called thermals. Visibility is excellent. Cumulus clouds are present in the sky. This is the time for experienced cross-country pilots to fly. However, these conditions may not be suitable for inexperienced pilots and must be treated with a great deal of respect. By now, you should have an overall idea about the movement of air on a planetary scale. Let's now turn to micrometeorology, the motion and forces of air on a much smaller scale. Understanding certain micrometeorology principles is extremely important because they directly affect the quality and security of your flight. Your familiarity with the weather will increase with experience. Nevertheless, as with any discipline, you should be curious about it and you should already be observing your environment in order to better understand it, but also later to be capable of evaluating current and projected weather conditions so that you know when to fly and when to stay grounded. Now we know that the air we're flying through is in perpetual motion and that there is no such thing as perfectly calm air. Disturbed and chaotic air currents called turbulence can occur, as can more orderly updrafts of air called lift. Lift enables you to keep flying for long periods of time. There are two main types of lift. Dynamic lift is created as wind flows over hills and mountains. Thermal lift is caused by radiant heat emanating from the ground. First, let's look at what causes dynamic lift. When an air mass cannot go around an obstacle such as a mountain but is forced to pass over it instead, the wind that climbs up over the obstacle creates a dynamic lift. Unfortunately for us, all obstacles and the air streams they generate do not create exploitable dynamic lift. In order to create good dynamic lift, three conditions are required. First off, the airstream must be as perpendicular as possible to the obstacle. Secondly, the wind mustn't blow too strongly, otherwise it'll become turbulent as it travels uphill. Lastly, the shape of the obstacle. The shape of the obstacle is essential because the air will always find the shortest means of overcoming the obstacle. In the case of this conical hill-shaped obstacle, the wind follows the most direct route around its sides. In the case of a sufficiently wide and reasonably high landform, the wind stream climbs over it and lift is produced just before its summit. Let's look at how an airstream advances uphill and downhill. It's important that you understand this phenomenon, not only to make better use of the lift, but also to avoid the hazardous areas. A lift originates on the windward side of the mount near its summit. The higher you ascend in the lift zone, the weaker the lift becomes. To take advantage of the lift, you should make figure 8s parallel to the ridge, making sure to turn with your back towards the elevated ground. On the leeward side, things are completely different. The airstream does not create upward lift, but rather downward moving air currents that are very turbulent. The further you descend into this zone, the stronger the downdraft becomes. The presence of turbulence makes flying in these areas extremely ill-advised. Flying through dynamic lift will result in your first long-lasting flights. Taking advantage of this kind of lift is not difficult. It will give you the chance to get used to piloting your wing so that you will be better prepared for thermal lift. Thermal lift is another way to make your flights last longer. Warm, invisible air masses of different sizes will lift and carry paragliders up into the clouds. We're not going to give you a detailed technical explanation on how to take advantage of a thermal lift, nor how to fly in thermal lift conditions. However, we do want to provide you with some essential information that will be useful to you later on. How are thermals formed? Remember back to the different energy transfers we discussed earlier? Thanks to radiant energy from the sun, the ground is heated up. It should be noted, though, that this depends on the terrain. For example, a ground covered with snow will reflect more than 3/4 of the radiant heat as opposed to absorbing it. Afterwards, the ground will conduct its accumulated heat to the air directly above it. That heated layer of air will become warmer than the air around it, and as it warms, it becomes less dense and inevitably rises through convection. A difference of 2 degrees is all that's needed to make this pocket of warm air rise. If certain pressure and humidity conditions are reunited, a cumulus cloud will form at the top of the lift. As soon as the lift stops, the cloud is no longer supplied and it will eventually disappear. For paraglider pilots, the cumulus is the king of clouds. It is the sign of good flying conditions, and above all, it indicates the presence of thermal lift. But there are also other clouds we need to be aware of. Distinguishing clouds is a difficult task because of the vast number of different observable cloud formations. This is why we're going to introduce you to the main clouds in each major family. Being able to recognize the clouds in the sky is very important before your takeoff, but also for anticipating the way the weather might evolve during your flight. Meteorologists have classified clouds according to 2 criteria: their altitude and their form. For the altitude, they have divided the troposphere into 3 layers. The lower layer from 0 to 2,000 meters, the middle layer from 2,000 to 7,000 meters, and the upper layer from 7,000 to 11,000 meters. We can identify which layer a cloud belongs to by its prefix: cirro for the upper layer, alto for the middle layer, and the absence of a prefix for the lower layer. The second criterion is the form. 2 main cloud forms are distinguishable: layered clouds, which are referred to using the word stratus or strato, and accumulated clouds, the word cumulus and cumulo being used for them. Within the upper layer, we see cirrus, cirrostratus, and cirrocumulus clouds, which are mainly composed of small ice crystals. Notice the 2 letters you see before the name of each cloud. They represent the international abbreviation for each particular cloud. Within the middle layer, we find clouds composed of water droplets called altostratus or altocumulus. Finally, we see stratocumulus and stratus clouds at the lowest altitudes. Since we glide at that altitude, these are the clouds we usually pay attention to. Stratus clouds are the lowest. They form fog or white blankets of mist at the bottom of the valleys in the morning. Stratocumulus may at times cover the entire sky. They are generally grey. Then you have cumulus clouds which develop throughout the day due to thermal lift. This is why they are a paraglider pilot's favourite clouds. Finally, there are clouds with an impressive vertical development, such as cumulus congestus, nimbostratus or cumulonimbus. These clouds belong to several levels at the same time. Cumulocongestus are cumulus clouds that have kept on developing vertically. Their bulging shape is typical. At this point, they become very dangerous clouds for our activity. A nimbostratus cloud is very dark at its base and quite thick. It's a rain cloud. Because of its strong vertical development, and more so because of its lack of visibility, it is a dangerous cloud for free flight. Then there are cumulonimbus clouds which can develop and extend as high as 12,000 meters. This cloud is by far the most powerful. You're better off admiring this type of cloud from the ground. For mountain flying, when flying early in the morning, you need to wait patiently for the sun to warm the hills because this is what creates the first breezes of the day. Let's look at how breezes originate and how they evolve throughout the day. Breezes are a localized phenomena that depend on a specific location's topography, vegetation, and most importantly, its exposure to the sun. Throughout the day, the sun will warm the hillside, causing the ground temperature to increase more rapidly than the water temperature. These conditions are what causes a breeze. The ground will warm the air above it through conduction, making it less dense or lighter and causing to rise. The result is a lift. And since nature hates vacuums, the space left free by the ascending air must be filled. The land in this case becomes a vacuum, sucking in air from the sea. A sea breeze fills in the void created by the convection. At night, the exact opposite takes place. The land cools much faster than the sea, creating the necessary conditions for a new breeze. This time, the air over the sea is warmer, hence it rises, generating a vacuum that sucks the air from land out to sea. This is called the land breeze. It usually isn't as strong as the sea breeze. Let's observe how the same phenomena occurs during various landforms, starting out with the morning. The radiant heat from the sun warms the eastern-facing hillsides. The hillsides then conduct that heat to the air above it. This air, having been rendered less dense, rises up the length of the hillside. These are called uphill breezes. Learning how to paraglide under these conditions is ideal. The gentle, uphill breezes will help inflate your wing, and you will experience little turbulence in these slightly elevating air masses. Throughout the morning, this phenomenon increases in intensity until around midday. This is when the sun is almost vertically overhead, which causes the greatest uphill breezes on the southern-facing hillsides. These breezes, called valley breezes, move in to fill the void left by the rising warm air. Late in the afternoon, the eastern-facing hillsides begin to cool off and the air becomes heavier. This air falls down the hillside, creating downhill breezes. These breezes help fill the void in the valley, as well as the one created along the sun-exposed westward hillsides. At sunset, air temperatures at higher altitudes are cooler than those in the valley or along the plain. Downhill breezes move in to rebalance the system. Certain phenomena, such as turbulence, can make a flight uncomfortable and dangerous. You should be comforted by the fact that during your training you'll be flying under calm conditions and on familiar sights, all the time accompanied by experienced instructors. Nevertheless, recognizing and understanding these hazards is the first step towards knowing how to avoid them. Let's begin by looking at turbulence. Turbulence comes from the chaotic movement of air within an air mass. They can be divided in two main types: obstacle turbulence and shear turbulence. Let's first look at obstacle turbulence. When the wind blows over an obstacle unevenly and discontinuously, turbulence forms. Air constantly flows up to the top of the windward side of this landform, but as soon as the air passes over to the leeward side, a depression forms, generating turbulences called rollers and rotors. There may also be areas of the windward side where turbulence occurs. For instance, if the windward side is hilly or irregular, turbulence will form in the immediate vicinity of the obstacle. Of course, in some cases, the obstacle generates no turbulence at all, neither on the windward side nor leeward side, such is the case here, where this particular landform creates a dynamic lift. Similarly, the airflow on the leeward side of obstacles such as a hedge of trees or a house can also be turbulent. For this reason, landing downwind of such obstacles is not recommended. Let's now turn to the other type of turbulence, shear turbulence. Shear turbulence occurs where two air masses move against one another. This is the case around a thermal lift, since warm air rises in the center and cooler air descends around it. When you fly into a thermal, you will feel the effect of this shear turbulence on your wing. Another example of shear turbulence you're likely to encounter when flying is the case of two superimposed air layers that are moving in opposite directions. Shear turbulence is present along the border separating the two layers. When a fluid such as wind passes through a narrow or restricted passage along its trajectory, its speed increases. This is known as the Venturi Effect. Let's use the example of wind blowing over a hill. At point A, the lower and upper winds are traveling at the same speed. At point B, the lower we descend into the air mass, the faster the wind speed is. Notice that the winds closest to the hill are the fastest. In fact, the wind is being compressed between the hill and the weight of the atmosphere. At point C, near the top of the hill, the speed is the highest because the atmospheric weight forces the wind through a narrow passageway. So as to ensure a constant flux, the wind is forced to catch up by accelerating. We also see the Venturi effect occur when wind travels through a mountain pass. As the wind blows through the pass, the airstream will be compressed. Like the wind blowing alongside the hill, it will also speed up as it makes its way through the narrow passageway. The wind gradient is the variation of wind speeds at different altitudes. This phenomenon is present at any altitude in our atmosphere, but the wind gradient we are interested in is the one where wind speeds decrease at low altitudes close to the ground during our landings. That is, at altitudes less than 50 meters from the ground. Why does the wind speed slow down? The air is a fluid with a certain viscosity that sticks to obstacles. In doing so, it loses a lot of its energy. The further we descend, the slower the wind will blow because of the gradient effect. This effect is present on fields full of obstacles such as hedges, but be careful. It may also be present on flat, obstacle-free fields. During landing procedures, the pilot must be extremely vigilant when dealing with the wind gradient. As soon as the wing encounters the gradient, it will lose relative airspeed. The only way to make up for the lost speed is to lose altitude. The wing will accelerate by itself, and in some cases it will roll off. Maintaining a sufficient amount of speed during the final approach is recommended to deal with this effect, an effect that can be dangerous close to the ground. Make a note of the fact that the altitude loss is directly proportional to the gradient's intensity.